Okay, we need to pick up the afternoon session. Thank you all for getting back so promptly. Two of our members that have already heard as part of a subcommittee the briefing that's about to occur are going to step out for about 20 minutes so they could meet with some of the local NASA folks. They'll rejoin us in about 15, 20 minutes. And our next briefing is one of great importance. Obviously, it concerns the Constellation project, and we have several briefers who are going to be presenting. And Phil, let me ask you, who will be first? First briefer. Hopefully the briefer knows. Okay, I think you do.
I do.
Great, thanks. Welcome.
Yeah, it's Jeff.
Jeff, it's all yours.
Okay. Sorry. Okay. Let's see. We need to turn this on. Can you all hear me? Okay. Check, 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 check. That's better. Okay. Good afternoon, everybody. Thank you for this opportunity to bring you up to date on the progress of our Constellation plan. We've spent a lot within this environment talking about what could be done. We wanted to spend a little bit of time over the next 3 days talking about what we are doing presently. We, along with the charter of this commission, we were also given explicit guidance from Office of Dr. Holdren, essentially, to go ahead and proceed with our current program of record as it stands while this commission deliberates, and so that's what you'll see us doing and the things that you'll see here the next 3 days. The next 3 days we've set out, we've got a little bit of time with you at each center. Today we're going to talk about Project Orion and the progress that team has made. Tomorrow we'll hear about the Ares project and its status. We'll also spend just a few minutes talking about the Mars architecture work that we have done as it relates to informing the plans that we are making for the lunar surface activities. And then at Kennedy on Thursday, we'll have a segment of time with you to overview the ground operations infrastructure plans and progress there. We'll status you a little bit on the Ares 1X test flight that is in the midst of processing at KSC. Talk about the Constellation Space Technology, Space Transportation Program Office, which is a ops command, development command kind of model that NASA is moving to with respect to the way that we do spacecraft development versus spacecraft operations, and we'll have more to say about that on Thursday when we touch on that. And then some closing remarks Thursday. While here at the Johnson Space Center, of course, Project Orion is the largest effort that we have ongoing here as part of the JSC effort for Constellation, but we also have 4 other projects within Constellation that are also in progress. 2 projects that are executing, 2 projects that are formulating. The executing projects are the Mission Ops project. This is the mission control, simulators, all of the plan, train, fly activities that we undergo here, and that team is doing detailed planning not only in how to bring forward the next generation mission control center, but also informing the designs of the spacecraft and the rocket as we go forward. And of course the EVA project, which is our next generation spacesuit. Unfortunately, we don't have time to describe to you more detail about those 2 projects, but we can provide that offline if you wish. And then 2 projects in formulation: Altair Lunar Lander and Lunar Surface Systems. Both are projects in pre-formulation in anticipation of a lunar program. Around Constellation this week, just to give you a little bit of status before I introduce the project manager for Project Orion. The Ares team is preparing a test firing of the Ares 1 first stage out in Utah. There's a 5-segment motor sitting on its side on the test stand, all instrumented, and that will be fired August the 25th. Down at KSC, we're stacking, as I said, the Ares 1X test vehicle. We've got the solid motor fully stacked, and this week we should commence with stacking of the upper stage simulator. There'll be more about that in tomorrow's briefing, and then a processing status for you on Thursday. We just released the Exploration Ground Launch Services request for proposals to industry. This is the ground operations processing contract that is out for solicitation at present. And then here at the Johnson Space Center and really across the country, we have the Orion team in the midst of conducting their preliminary design review. And to tell you more about that and more about the Project Orion progress is Mark Geyer, the project manager here at JSC. Mark?
Thanks, Jeff.
Good afternoon. My name is Mark Geyer. Obviously, I'm the project manager. I've put together a presentation with, I think, the key points about Orion, but obviously the presentation is for you. If I'm missing something or have a question, please don't hesitate to stop me. Let's go ahead to the first chart. Some of the key points I'm going to talk about today is Orion is part of an architecture, so its design is driven by the architecture in which we function. Second of all, we are completing the preliminary design review. The board is actually the end of August. I'll go through the details of that. We've completed significant and extensive engineering and development testing. You'll see some of that in this presentation. We're also optimizing the details of our 2015 launch date, and we're using a risk-informed design to build a safe vehicle and ensure mission success. And we've already started production. So you'll see all those key points in this presentation. We'll go to the agenda next. So I'll talk about an overview of the vehicle, talk about PDR, talk about the progress in our hardware development, the schedule, mass management, human rating, and I'll give you a summary at the end. Next page. I think people know, go ahead and go to the next page. This is an overview of the Orion system. It shows the launch abort system at the top. This is how we get the crew module off the stack in an emergency. You see the crew module itself and the service module below that provides support function and the spacecraft adapter that links us to the Ares launch vehicle. I think an important point I'd like to make here is that in this integrated Orion system, the focus is really the crew module. The crew module is where the crew obviously is, unless they're in the lander on the surface of the moon. So it's a focus of our crew safety discussions. And it's also a big mass driver, the mass of the CM. The CM is the one element that goes all the way to in orbit around the moon and then actually returns to the surface of the Earth. So every pound that's on the crew module is multiplied many times in the architecture itself. So that process drives really that only key functionality that's needed in the CM for CM operation and for crew safety remains in the CM. There is no superfluous bells and whistles and other functions in that element. The next page, I'll show you a little bit about the architecture I talked about. We are a lunar-capable vehicle that can also support ISS. So on the bottom, you see the Orion there after launched on Ares 1. Can dock and be used for crew supply and also stay the full 6 months. And at the top, we are part of the lunar architecture in conjunction with the EDS and the lander you see going to the moon and then orbiting the moon while the lander goes to the surface. Next page, this architecture is a robust architecture and it actually enables extensibility to other missions. And so we talked about a few of those things. Some of those will require some upgrades, but actually the Orion capability gives you a lot of functionality that can be used for these extensible missions. What I'd like to do next is I'll go through the specific elements and talk about them and talk about a little bit about where we are and what's driving them. So if we go 2 pages to the crew module chart, thank you. I talked already that the crew module is unique and it's the one element that is launched from the surface and actually returns to the surface of the Earth. It also acts as our docking interface to the space station and the lunar lander. And it carries the 4 people to the ISS and to the moon. On the lower chart, you'll see pictures of the flight test article that we're actually going to fly for Abort 1. And it gives you a rough idea of the size and the mass properties of the vehicle. Next page is another picture relative to the CM. We talk a lot, I'll show you some pictures of hardware, and sometimes it's hard to really convey the amount of work that goes into the analysis to come up with a good design. And I think this is a really cool chart, but that probably says more about me than about the chart. But if you look at the pressurized element within the Orion, which is on the left, you'll see I've pulled that out on the upper left of that box. It's a key piece, obviously, because the crew resides in there, and it becomes one piece of structure, but it is driven by, again, because it has to fly the whole mission to the moon and back, it's driven by 5 different load cases. In other words, there are pieces, different pieces within this structure that are driven by different load cases, and we have to optimize for those load cases. At the top, you'll see that the docking interface is driven by the translunar injection loads. A little lower than that, driven by abort ignition from the last, when we have the abort case where we need to pull the CM off the stack. Below that, the structure is driven by internal pressure. Below that, it's driven by water landing. And then at the top, we have some combination also with drogue chute loads. So, number one, it's a structure that needs to be well integrated, well designed, and it takes a lot of analysis to figure out what those driving load cases are. So let's go to the next page and show you a little bit about how that comes about. So you start out with your design. You obviously have to turn that into models. You have mass properties and today we have a 4,000 line item master equipment list by component, down to the structure and secondary structure. Then you develop finite element models, as you know. Then we fly those through the mission design trajectories. We have to understand how the propulsion system works, what loads they drive into the vehicle. We do wind tunnel tests to understand the aero loads, which are difficult to predict in computer modelings, in the special cases that we fly. Then we roll that into a loads analysis, and that's what drives the design. There's a couple things I'd like to pull on. For example, I mentioned that the bottom of the spacecraft is driven by water landing loads, but it's actually much more complex than that because there is not just one water landing case. The nominal, we assume, lands in a sea state 3, which are relatively calm waters, but we have to assume that we can handle one parachute failing. So it's a 2 parachute case with one failed out. So that drives certain loads. We also have an abort case where I can assume I have all 3 chutes, but I land in the North Atlantic, so it's a sea state 5, waves as high as 10 to 12 feet. That drives different loads into the vehicle. So you have to understand that full range of cases. You have to run those to really define the driving loads and then affect the structure based on those. The same with launch abort. There's not just one launch abort. We can abort off the pad. We can abort in a transonic mode. We can abort at max Q. All sorts of different abort modes which drive different loads into the vehicle. You have to do all that analysis with the proper models for the launch abort system to understand fully what your pressurized structure is going to see and design it appropriately. So we've done that work over several DAC cycles, and we have a primary structure that we've shown works, meets those requirements, and will get us ready to build. In fact, I'm going to show you that we're already building a ground test article today at Michoud that we're going to test. So we're well on our way. Next page is another example of the complexity of integrated analysis that needs to be done in a vehicle like this. Power and thermal are very complicated, not because everybody understands they got solar arrays and batteries, but you have to take your component list. You have to understand when they need to be turned on, so you need a mission timeline. You need to understand how much power they're going to draw, so you need to calculate those things. You need to understand what attitudes you're flying, which affects obviously because the sun heats the vehicle differently. So we've run Orion through all the space station cases, through all times of the year. We've run it through flying to the moon at all possible solar locations, and even in our failure cases, and identified that we have a power and thermal system that closes. So now I'll show you a little bit about the hardware. If you go to TPS, obviously TPS gets a lot of attention. It's a very dramatic environment, very hostile environment. We started out with 6 different materials. The NASA team, which has great experience with TPS, led that. We did hundreds of ArcJet tests and down-selected to 2 materials, and then eventually down-selected to 1, which is Avcoat, which is similar to what we flew in Apollo. We used figures of merit like reliability, maintainability, manufacturability, thermal properties, and everything else, and Avcoat was the clear winner. On the back shell, we're using a tile similar to shuttle. It gives us the thermal properties we need, which is a much less challenging environment on the back shell than it is obviously on the heat shield. And also this particular material is much more resilient to MMOD strikes than other materials we examined, because now we have to not only consider its thermal properties, but also the fact it will be on ISS for 6 months. And so it needs to be able to be more resilient to MMOD strikes. The other thing I want to mention is that we have a vehicle both in the back shell and the heat shield that are built for both ISS and lunar. This heat shield is built to withstand the heating we're going to see on a lunar reentry. So we have one system to do both jobs. Next page. Talk a little bit about docking. As I said, this is our docking interface to ISS and also to the lander. We have a low-impact docking system that's developed here at JSC. You'll see a picture of the capture ring. And this team's already built an engineering development unit for a similar design. Crew cockpit interface, next page. Obviously, the layout is very important. The crew needs to be able to see all the displays and be able to handle cases where, for example, one display goes out and they still need to be able to see the other two. So the layout is very important. We've done mock-ups looking at these layouts we've actually designed now, and you can see in that bottom picture we actually have a hardware now for these display units. That's one of 3 that we'll be flying. These display units are already in test for nominal loads and abort loads. Next page is the service module. Obviously a very critical element. Not only does it do a lot of our propulsive maneuvers for ISS and lunar, but it also is a big part of our abort capability. It allows us to abort after the LAS has left. It can get us to orbit, and abort to orbit, or actually get us to Ireland or back to Newfoundland and keep out of that worst case North Atlantic zone. So it's a very important system. In that case, also does our power storage and consumables. We also have the capability to accommodate unpressurized cargo in the back end. So where one of those radiators on the bottom would not be needed, there's locations in there for the ISS version, which has only 2 tanks instead of 4 needed for lunar, where we can launch ORUs for the ISS or unpressurized payloads. And at the bottom you can see we're already testing auxiliary thrusters, solar arrays, RCS thrusters, and there's an example of the tanks that we're going to be flying. Next page is the launch abort system. Again, this is a key element for us to meet our safety goals, to be able to get the crew off the vehicle if there's a problem. It's a 3 solid rocket motor system for the reliability. The first one is, we call the abort motor. That's the one that gets you off the stack. It's 500,000 pound thrust. The next motor up the chain is the jettison motor. That gets this ALAS structure off the crew module, both in a nominal flight, if we don't need it, and also after an abort. And then at the top is an added 2 control motor that allows us to fly in these difficult regimes to minimize the loads, and also orients the vehicle before we pop the top off and actually deploy the chutes in the right attitude. And I'll show some of those actually that we have built and fired. The next page, I wanted to talk a little bit about, there's a whole bunch of other stuff, so I was trying to figure out what would be good to focus on. I'm going to talk about the safety analysis, but we do a lot of other analysis that I think is important to ensure that we have a safe and reliable vehicle. Obviously, we do a lot of abort coverage, gap analysis, so we can make sure that for every phase of flight of the launch vehicle that we can get the crew off in emergency. We've done that. We have no gaps in our abort coverage. We do landing accuracy analysis to make sure we know where we need to land in Southern California so that Pepper's recovery guys can get us in time. We've done that analysis. We meet the requirements for landing recovery. We obviously calculate crew loads at landing, because it's not just important that the vehicle structure survives, but that we understand the loads on the crew. We've modeled that extensively, and we've also meet those requirements. While I go to the next page, let's talk a little bit about PDR. PDR is a critical milestone in the development of any vehicle. The criteria for PDR are not defined by Orion. They're actually set by the Independent Technical Authority at NASA. And they're very rigorous to make sure that we felt comfortable we had the right vehicle and that our customers did. We set up a set of documents to be delivered and also a set of reviews to be held to go over that design, which culminates again in the PDR board, which is at the end of next month. So we've had many reviews. Go ahead into the next chart, sorry about that. So we've had lots of technical peer reviews. Those are really tabletops where the engineers get across the table and go mark up the design and ask each other questions. So that those we have completed. We had 18 subsystem design reviews, 16 of which were in a 2-week period in Denver. And I think this is probably a good time to talk about what happens in those design reviews. So it's a large number of experts. So, for example, a subsystem design review would be the key subsystems, ECLSS, GN, and C, for example. So I think of the ECLSS subsystem design review where at that meeting, not only were the key Lockheed designers and their subs, Ham Sundstrand and the other people that were there, that are key to building the hardware, but also the NASA expertise over the last 40 years, people who had been part of Apollo, people who had flown and built the shuttle hardware, people that had been part of the space station ECLSS system were in the room critiquing the design, adding suggestions, not only design but also in test, which to me is a critical part of this process, that those teams are embedded together working through these issues, because that gives me much more confidence that we're using the lessons that we've learned in those past systems to make sure we have fewer issues as we go forward. So the next big review we had was a system and module review, which is we talk about the integrated products, power balance, integrated thermal, integrated loads. That was done about a week and a half ago. That was completed. So now we're in the process of reviewing the documents and heading on to the PDR board at the end of August. Next page. I want to give you some pictures of the hardware, but I want to start with this one because this is a great picture of the assembly area in Michoud in Louisiana. You'll see the tooling on the left, and actually parts of the ground test article for the crew module are actually mounted there and being welded. So we are on our way producing this vehicle. Next page. Obviously, it's essential that when you fly people, you need to be in a position you can say that people can actually operate the vehicle. It's important to do that very early. We've been doing these kind of evaluations since 2005, but just to give you a snapshot, since April 2009 alone, we've had 47 days of testing. We've had the crew in there again looking at viewing, stowage, and emergency egress to make sure that if there are any fundamental issues with the vehicle, we can get it now before PDR. The next page is post-landing recovery. We built a Orion mock-up here where we actually were able to take it out into the waters, into the sea states we're going to be seeing, had actual recovery forces participate in that, looked at what it took to actually install the flotation ring, how hard it was to get on the vehicle. We looked at different ways to stabilize the vehicle. So again, great data now before PDR to help us design the best vehicle possible. Next page. I talked a little bit about landing. We've done a huge amount of drop tests, both when we were looking at airbags and retro rockets, all sorts of soil characterization. What we show on this page is the most recent testing, where we're looking for a test fixture that allows us to calibrate the struts. So we have, within the crew module, obviously we have a crew pallet. That crew pallet then is attached to the structure with struts. We use this to calibrate those to make sure we understand fully in real drop tests that we can calibrate our analytical models to make sure we're calculating the crew loads effectively. So a great move by that team. Parachutes on the next page are obviously key parts of the architecture. So we've already had 15 drop tests, both single tests as well as cluster on the drogues, the mains, and the pilots. So again, much more testing to go on here, but well on our way. Next page, the solar array deploy. That you may recognize that this solar array looks similar to what was flown on Phoenix. So we're modeling the size that we're going to see on Orion and did a deployment test on this mechanism, and it worked very well. Next page. Okay, we'll talk a little about the fire and smoke. Again, this is the Abort motor. The first upper left is the attitude control motor. That's a single valve. The attitude control motor actually has 8 valves, so that's a single test, single valve, full thrust. The jettison motor on the right then is a full-scale jettison motor. We fired 2 of those, and then the Abort motor on the bottom is the 500,000 pound, and we fired that one last year as well. So for the jettison motor and Abort motor, we fired full scale. They're ready to go, and actually we have those guys at Wismar today. The attitude control motor will be firing a full 8-valve ACM at the end of September. Next page. So this is a little bit about Pad Abort 1. So this is the, again, Pad Abort 1 is one of our abort tests we're going to use to verify and validate our abort plan. The Pad Abort is one of the most stressing cases in that we need to get the the abort motor needs to get you high enough and far enough out that you can make sure you can deploy the parachutes before you hit the water. So it's an important test for us. Langley Research Center built this crew module. It's now got the avionics. We can go to the next page. There's more testing, and on the left you can see the real flight hardware for the jettison motor and abort motor on the left, and the crew module going through integrated testing on the right. Next page is a picture of the avionics that's installed within the crew module. All that is going through its final testing now. And then the next page is the facility. We're doing these abort tests at White Sands Missile Range, much like Little Joe was done in Apollo. In fact, you can see that facility not far from where we're launching our stuff. On the lower left is actually the flight integration and test facility. We are actually assembling the launch abort system in that building, much like exactly the way we'll assemble it at Kennedy eventually. The mobile ops flight test control room is basically a trailer. You see it down in the middle there where we do our flight control. So we can actually, we've had that at Dryden checking out the system. Now we can roll it to Wismer and actually use it for the flight itself. The gantry at the top is actually going to be used for ascent abort to assemble the vehicle. So the facility for Pad Abort 1 is ready to go. Next page, NASA did an investigation, or actually a competition, to select the facility we wanted to do our qualification in for this vehicle. And we wanted this particular facility was picked in large part because we were able to do all the key tests within this one facility. This is obviously at Plumbrook in northern Ohio. It's also sized not just for Orion, but also for the lander itself. So we've worked with Level 2 to make sure that the requirements for both are incorporated. Lower left is the vibe table under construction. Then on the right are two different pictures of getting the acoustic chamber built. Relative to production, if we go to the next page, how are we activating our production system? The ONC building, I don't know if you've been at the Cape. I guess we'll be there in 2 days. But you'll see lower right is actually a picture of the ONC building, and if you've ever been there before it was completed, you know how much work was done both here, and you can't see the basement, which is also an incredible amount of work. That building was completed below cost and ahead of schedule. Great job. And the tools now are being designed for the ONC. Lower left is, again, MAF, the chute assembly facility. You'll see the tooling there, and our welding fixture is up and ready to go, and we're using it today to build the GTA. At Kennedy, we'll be using the canister rotation facility for assembly of the LAS, and we're in process of making the minor mods necessary to get that building ready for production. Next page. So how we're using it. The GTA is obviously being used at MAF, being built at MAF. We're using launch abort procedures at Wismer to actually assemble the launch abort system, so we're actually doing that production. The service module is we're still in design for its GTA and getting its tooling finally completed. On the next page, since we're talking production, I thought it would be good. Again, easy to show hardware pictures. The question now is, what are we doing to minimize the life cycle costs? What are we doing today? It's easy to think about at the end. What are we doing up front? What I tried to show on this very, very crowded chart is a couple of things. Upper left is we track on a monthly basis where we stand relative to days in the critical path in the assembly. So this is our metric to say, are we as lean and as streamlined as we can possibly be. On the lower left is a list of structured improvement activities, Kaizens, Lean Six Sigma, other things that have been done relative to all the different production phases. So we've done a lot of those. And on the right are specific improvements incorporated into the vehicle design, either in the building, in the Orion itself, or in the ground support equipment. The last page then is on this stuff is basically that production has started. So go one more page, sorry. There you go. Again, more pictures of the production and the welding that's being. So that upper right is just a picture of the friction stir weld. It's a part of the, as we put together the ground test article. The ground test article will start. The first test we'll do is put it in through an acoustic chamber to make sure we understand how it transmits the acoustic levels we think we're going to see. And then we'll also use it in our drop tests to make sure we calibrate the structure to the landing loads that we think we're going to see. Next page is, and we'll give you a sense, so I've showed you a lot of analysis, a lot of hardware, so where is all this work done? These are all the locations. You can see the NASA centers, you can see the key areas where Lockheed is located and also its major subs. So it's across the country. Roughly about 3,100 people work on this project. About 10% of that I would classify as oversight. There are about 800 NASA folks, but the majority of those NASA folks are actually producing products. The parachute system, worked on TPS, working on the docking system, also part of the GNC MO team, working on the things that NASA knows how to do. But oversight itself is only 10% of that number. So next I'll go to the schedule. So yeah, go ahead one more page. So what I'm going to do is kind of describe the critical path and build it up for you. I'm going to start from the launch date and go left, talk through each of the major functions, what we've done to streamline those, and what we're doing to give us more and more confidence on this launch date. So if you start on the lower right, you see the launch date of Orion 2, our commit date now at March of 2015. Go ahead, another click. There you go. So you see those launched. So at this time, Pepper's guys are assuming around 6 months processing. So we hand off before that. If you go to the next chart, what we have done is we push that further to the left. We are being more aggressive on the schedule to give ourselves more runway in front of us. So we're actually going to deliver the vehicle ahead of when ground up's needed. So we're going to deliver in June of 2014. What that does then is that pushes the rest of these milestones to the left, and we'll talk about that. The next thing, if you look at that chart and you see that the dotted red line, it turns out that the critical path is not in the assembly of Orion 2, but actually qualifying the design prior to launching Orion 1 and Orion 2. So what we need to do in the critical path now is move up to the system qual, which is basically a flight element going through qualification. So on the next, go ahead and click it one more time. You'll see it right there. System qual prior to Orion 2 delivery for launch processing. So I will break that down for you, and you'll see the pieces that go into that. Now, before we can qualify the flight vehicle, we have to build the flight vehicle. So the next piece is AI&P, which is assembly, integration, and production. So go ahead and hit the next. There we are. So I'll talk through exactly how we come up with that schedule. And then before we can assemble the vehicle, obviously the components need to be fabricated and delivered. So one more click, and there we are. Okay, so I'll walk you through each one of those. I'm going to start off again with the flight qual on the next chart. Okay, so this shows you for the flight element, it arrives. We do the assembly because we ship it in pieces, the SM, CM, and the LAS. We do a final assembly, then we go through vibe, we go acoustics, we go pyroshock for the SM. We do pyroshock for the other pieces, SMSA, we do thermal vac, we do EMI, EMC, and then we do pyroshock between the CM and the SM. Then on the next page, we do fairing separation, we do lightning, we do vibration, we do pyroshock for the separation with the other systems at landing, and then we do human in the loop demos to make sure we verified all the requirements for the human interface. So that's a lot of stuff. That's a lot of testing. It is right now a serial process where we bring the flight element into that system. Right now we're looking at, if you can see that we believe the tests needed for Orion 1 qualification end after the SM fairing separation because Orion 1 is unmanned. It's also a flight test. So now there's further testing then required between that and the launch of Orion 2. So we have defined these specific tests in detail. We've defined these durations in detail. They're rounded up to the nearest month just because the chart got too complicated. So it gives you a sense about how long these tests take. We are working now to make sure we understand, are there ways, and actually we have some ideas, are there ways to get some parallelism in the schedule? In other words, take things out like SM fairing separation and actually do that on the structural test article so that we're not waiting on that to qualify the vehicle. Also, we're looking at ways for the ECLS system to actually do a test bed offline from this to actually do its qualification as well as integration with EVA. So again, it would take some of the schedule criticality out of this. So we have a plan. It fits. We're working hard to find other ways to add confidence to the schedule by removing some of the serial nature of these testing. Also, there's a lot of, we need to look hard at what are really the requirements for launching Orion 1 since it is unmanned and it is a test flight, and how much of that test flight experience we can actually use in our qualification. Okay, so now we have a qual plan. Now we need to go to how to assemble that vehicle. So go to the next page. This is the factory again. I showed you a photo of the real factory. This is a layout where the different stations are. I won't go through this, but we take this. Then the team, as I mentioned, very detailed analysis talks about then where the components need to show up and where they're assembled, and that generates the next chart, which is the schedule chart for this assembly and integration and production flow. So on the lower right, you can see the qual test itself. So we're building up on the upper part the CM, on the lower part the SM. It talks about every station. It talks about every task. It talks about where each component needs to show up to give us the best assembly flow. So now we take this, and it drives the component need dates. And if you go to the next chart, we get very detailed schedules on each component. This is an example of only the CM, some of the CM items. As you can see that in the details. Again, it's hard to read, but I wanted to show you that we are at this level. In fact, this is only one page of many showing, lining out each of the 360 components needed to do this assembly. So we take this then, and we bang it up against, if we go to the next chart, each component, as you know, before you can go buy it, you need a spec, you need to turn on the contractor, and then you need to lay that in the hardware delivery date. So we take each one and work with the subcontractors on when they need to be turned on in order to meet the delivery date that we've been given. There are ways now to add margin to these as well. There's some flexibility in the assembly process. Those guys obviously optimize for what made sense for them, but we can talk about if I got one element that takes a little bit longer, we want to deliver that one later, that gives me some options there too. Most of these component delivery dates we got were delivered when the budget was much less in 09, in 08. The program has enhanced our budget, so now we have more money to help accelerate those components and give them some flexibility. And there's also some things you can do to stop pounding flat some of the mass things. For example, some pumps, you can go ahead and spec them at a wider range. They're a little bit heavier, 2 to 5 pounds, but rather than optimizing and analyzing to death, we can go out and buy the pump and take some mass inefficiency, but get the pumps moving. So that's another example of things that we can do. And we are doing that component by component to give us more and more confidence in our launch date. Well, if we go to the next page, so I think I summarized, yeah, go ahead, click off of that. So we did get significant more money from level 2. Some of it was stimulus money, some of it was money back from the pass back. We've used that money to increase the engineering development units, which increase our confidence when we build the production units, they're going to work. It also helps us by starting our higher critical path items early. As I mentioned, we push the delivery date to be 2014, mid-2014, even though it's not required. And we also push the AI&P guys to the left as well, even though it's not required, because I want runway in front of me, and that way we force out the big driver. So this work has helped us do that. I think that's the key for that chart. Let's go ahead, let's talk mass, because it's on everybody's mind, I think. Go ahead to the next chart. So again, I'll talk about where we are at mass, but it's also important to know that, again, this is not a high-level mass estimating relationship. This is generated by a 4,000-line master equipment list, detail down to the component about how much each one weighs. We do very extensive center of gravity measurements, ballasting, so we understand how much ballast is necessary to meet our L over D requirements. So when that is racked up, today, even for the previous, the 6-person crew design, we are under. In other words, we are 270 pounds lighter than our requirement. This does not yet even take into account the mass management, my reserve, my 2,000-pound reserve, or taking any credit for any of the mass growth allowance that we know we'll probably use, so we don't take credit for that. So for ISS, we are under. For the lunar, you see below that, we are 1,800 pounds over at this point in a 62,000-pound vehicle. Again, this does not. I have not used the 2,000-pound reserve, and I'm not taking any credit for weight growth allowance. I'm assuming I'm going to use all that, so that I need to find a way to resolve this 1,800-pound upper. There are ways to do that for the lunar vehicle. Several different things. We know that for Space Shuttle and also Apollo, at the beginning they were all heavier. We learned a lot about the structural efficiency and structural factors of safety that we were able to back off on once we actually saw the real loads when we were flying, and reduced several hundred pounds in both of those programs. We expect to see that in this case as well as we fly the ISS mission. We know we'll be able to take advantage of avionics upgrades. We have an open architecture. We know that avionics for Altair and so forth are going to be delivered, that we can take advantage of their mass reductions. And we have a significant amount, of propellant flexibility here. We're maxed for anytime return, any launch, any location on the moon. We're flying 18,000 pounds of prop, so there's obviously some flexibility there in the early missions of using some of that prop offload to help this issue. Let's go ahead to the next page, the human rating, because I think this is a very special thing about Orion and Ares 1 and this whole constellation architecture that makes us a little bit different. Let's go to the next page there. So there is a requirement, an NPR, that was released in May of 2008 that talked about the human rating requirements and fault tolerance, and it talks about that having at least a minimum of one fault tolerant, but basically using your brain, right? Let's figure out the right level of fault tolerance based on risk-based integrated design and safety analysis. Again, a very, very wise approach. NASA has generated a process for identifying this and making sure that we believe we meet the intent of this requirement. It uses PRA, probabilistic risk assessment, which I'll talk about in more, and a lot of the usual safety products, failure modes and effects analysis, reliability, other engineering analysis, hazards, and so forth. We've used these products iteratively. It's not like we just started thinking about them. They've been part of the process since the beginning and have actually influenced our design quite a bit. Let's go to the next page. The other important thing I think to mention is that Lockheed and the NASA Orion team do not get to by themselves judge whether we have met the intent of this requirement. I mean, we are obviously a key part of that. We need to be comfortable that we think we've met the intent and that we believe the crew is safe. But there is an independent, totally independent safety panel at the Constellation that makes the final judgment on whether we have met the intent. Part of that process is a Phase 1 safety review, which there are 78 hazards that we have actually identified and developed mitigations for that are in process of being reviewed. 57 have been reviewed today. We also use the other safety products to help us identify the risks and use them in our design process. For example, there were 4,500 preliminary FEMAs developed and reviewed for PDR. We use the SILs in the subsystem design reviews. Again, the engineers need to take ownership for these safety products. And the chief engineers meet and go over the vulnerabilities list to identify ways that we can fix these vulnerabilities at a system level before the design gets set. And for that process, over 60 design changes have been identified to reduce the risk of the crew and increase mission success. So it's a critical process for us. The last thing I'd like to talk about relative to this is probabilistic risk assessment, which is, we'll go ahead and flip to the next page. It's a great tool. It is, you need to be careful about fixating too much on the actual number. It's much more important, I think, much more valuable in the way of comparing relative value of choices that you might make. It also needs to be, this probabilistic risk assessment needs to be a validated model. In other words, you need to agree on the techniques, how you're measuring it, how you validate the data that goes into it. That is, again, a process that is validated and confirmed at level 2. It is not strictly an Orion process, so we get overviewed, we get audited, and confirm that we have the right technique. But then you can use that tool to do several things. Number one, it identifies the top risk drivers while you're in the design process. So the upper left chart is a loss of crew calculation and allows us to see that the key elements that are driving, in the ISS case, driving loss of crew are MMOD, the parachute architecture, the CMSM separation mechanism, and the jettison motor. So then we can take those and make sure we're attacking the right things when we go through our design process, and we've done that on those items. It also allows us to enable risk-based decisions. So on the upper right is a loss of mission calculation, because PRA is not just used for loss of crew, but also mission success in the loss of mission calculation. This is actually a chart used at our engineering review board at the end of last year, where they looked at specific detailed hardware changes and their effect on loss of mission, and also their impact on cost and mass. So we can make, again, are we balancing the risk correctly across the vehicle? So a great tool. And at the bottom says that it helps us reduce overall risk. That is our loss of crew trend. It shows you a couple things, both as the design changes were made and also as the model fidelity was wrung out. That's that little hump as we came over into the last part of DAC 3. So using this tool has helped us reduce overall risk to the crew. So with that, I think I'll summarize. Go to the next thing. So it's a fascinating job, and I think our team has done a great job and met the challenge of this complicated system. We have a lunar-capable system that will support ISS. It took a lot of rigorous system engineering to get a good design. I believe we have that. This risk-based process has given us a robust system and safe system, and we're working hard to lower the life cycle costs, and I've shown you some of those things. I think the other important thing is we have a stable design. We are in the process of PDR, but all the products that I'm seeing, and I believe when we come out of the board, we will show that we have a great design to move forward into production. And we've actually started production on some of the key systems that are the long lead. So with that, I'm done and open for questions.
Very good briefing. Les?
Mark, thank you very much. A very good briefing. I'm wondering, looking at schedule risk, contrary to most programs that I'm familiar with and I think had experience with, where program directors, program managers want to try to build as much margin as possible, you started, as you said, by fixing the launch date and then moving the key events back to the left, which actually takes margin away in a normal way of looking at things. And then you're trying to buy back margin by doing some creative sort of activities and experiences. Could you just comment on those two dichotomies just a little bit again? If you
I'm glad you mentioned that way, because I didn't communicate it very well. I did it as a communication tool to show you how things end up with the launch date. But if you saw that, we actually pushed dates earlier to give me margin at the end. So I pushed delivery earlier. I pushed AI&P earlier to give me margin on the end, which then made it harder up front, which is the way I want it to be, right? Because I got runway in front of me. So I just didn't communicate it very well. I backed it up so you could see how it linked to the launch date, that's all.
Okay, good, thank you.
Sorry.
I feel much better. Let me ask about PDR, though. Again, in my experience, very few new programs ever get through a PDR completely clean. Could you just comment a little bit on what kind of challenges or issues you came across in PDR and how you've handled those?
Yeah, very good. First of all, I would say we got into, I want to talk a little bit about last year, because we had a plan to do the PDR last October, and we looked at the state of the design and where we were, and it was the judgment, I think, of the whole team and with our management that we weren't ready, that we needed time to mature the design. So although there were systems that were ready, the full integrated system wasn't. So we've taken advantage of that, and that's why we're getting, I think the products we're seeing today are ready to go. But I'll talk about the few things I think we're going to see open. We know on the relative to design, the parachute architecture and how we deploy the forward bay cover. We have an architecture today. It's a little heavy. We're actually think there's probably a more simple way to go get that forward bay cover off. So we actually got a separate independent team looking at that and talking about how to improve that design. So I'd say there's an architecture thing that we're poking on. I think I talked about the qual test. We all want to give ourselves more margin in that qual testing bar and those things, but we also want to make sure we've qualified enough to make sure it's safe to put the crew. So we need special emphasis to make sure that we can close that and look at ways, as I said, to pull things off of that serial testing and get them off on the side parallel. So like the ECLS test bed, the moving fairing step off to the STA, we need to flesh those out and fit those into our budget plan. So I'd say those are the two big things I think we're working on.
Thank you.
Ed?
Mark, thanks for this thorough overview. I apologize for not being here for the first part of it, but I flipped back and didn't find the answer to this question, which actually has two parts that have the same ending. Let me explain the motivation for the question is that some have proposed, as a matter of fact, Steve Lindsay proposed before lunch that it might be appropriate to allow the commercial sector to take care of manned flight, human flight to LEO and the ISS, and reserve the NASA capability for what we might call the hard problems, going to the moon and beyond. So you as the program manager, I'd like to get some sense, first in sort of a rubber vehicle sense, in a sort of hypothetical sense, if you relaxed the requirement from going to the ISS off of the Orion, to what extent, if any, it would simplify the design? That's question number one.
Okay.
Question number two is, in the real sense of where you are today in the program, with all the contracts in place and test programs established and so forth, if you relax the requirement to go to the ISS from the Orion, how much it would simplify the program? You understand the two questions I'm trying to get at?
Maybe you could help me with the second one. I think I got the first one. If I
first
took
one
the
is-
ISS requirements off of Orion, how much would that help me? Was that
In
for the
principle.
list? Okay.
And in the second one is, based on where you are today, with a real set of hardware and a real set of design and PDR already, largely past you and so forth, how much it would actually help you.
Oh, great. Okay, good. I understand now.
So it's two quite different questions that end the same way but start
Okay.
slightly different.
I think, great question. Fascinating thing about the architecture is that actually a lot of the driving cases are similar. For the lunar outpost case, we are a 6-month stay around the orbit of the moon. The ISS case is a 6-month stay case as well, so they're similar in that case. So a lot of the systems, I would say, are actually sized by the lunar case, not by the ISS case. So, for example, for the service module in the lunar case, we fly 4 tanks. The ISS case is just 2 tanks, but of course we take advantage of that. We can fly payloads in the back end. So taking the ISS requirements off is not a huge driver, not a big driver for us, and I think you hit on it, especially not now. I have a design that can do both, and we're in the midst of testing it and qualifying, getting ready to fly it. So it would not help me much at all today.
Thank you.
All right.
Hey, Mark, good to see you again.
Hey, Leroy, how are you?
Thanks for your brief. As you were saying at the end of your presentation, mass and volume of the Orion drives a lot of the rest of the architecture. And, of course, what drives the size and mass of Orion, one of the big drivers is the crew size. And we've been asking the question, excuse me, we've been asking the question, where did this requirement for 6 crew come from, and could it be relaxed down to 4? And, in fact, of course, it already kind of has been, because for ISS, the requirement's 4, for lunar, the requirement's 4. And as Steve said this morning and other people have said, we're designing presumably the vehicle for the next 30-plus years. And a lot of your challenges may get a lot easier if we take a pause and say, well, do we need to, should we relax the requirement down to a crew of 4 and reduce the size and the mass? And, if that of course would have cost and schedule impacts, but in light of a 30-plus year vehicle, is that a fair question to ask?
Yeah, it's a great question. So actually the program, in concert with headquarters, has agreed that we have a system. I actually have a PDR design that'll accommodate 6 people. But they've agreed that since the ISS mission is really 4 and the lunar mission is 4, that we focus on flying that mission. So that gives me some flexibility. on the life support system, for example, some choices I can make there on mass. Rather than continue to pound flat and file everything, right? I can use that mass, some of that mass, to help me get moving. Others I can use for ISS payload. So basically, headquarters and the program have given me that flexibility today to assume 4 for ISS.
Okay, but really what I'm asking, I guess, if we change the mold line to a smaller base and make the overall mass of the capsule even smaller, I mean, is that a fair question to ask?
Yeah, I can tell. And I'll answer it because it was a great question about what that means today as opposed to what it might have meant 4 years ago. If you looked, Leroy, I think the way I'd look at that is if you remember the chart I had that showed the pressurized vessel and all the analysis that goes into determining what the driving load cases are and how you have to turn that into design, do a finite element model, do the load cases, plus the fact that I would have to redo the packaging. The packaging is very important for CG and so forth. And just because it's smaller, the system size and mass and volume is not going to change significantly now that I'm at 4 people. Because again, a lot of that was driven by the lunar case. So I'm going to have packaging issues with a smaller vehicle. But to redo that, to redo the design, to redo a finite element model, to redo the loads cases, I can do it. But it would be a significant schedule setback, and like you saw, I'm already building the GTA to the design I have today.
Okay.
So it depends on when the question was asked. 4 years ago would have been different.
Sally?
Okay, I have a quick follow-up to Leroy's question, because we've been hearing a lot from a variety of different people about the importance of calculating life cycle costs, and that it's always the tendency to try to minimize the development cost, but then you end up paying for it in the end with the ops costs. And I wonder whether you could address, or whether you have thought about, or anyone in the program has thought about, if you're wise, you've probably resisted even thinking about this, but if the capsule were smaller, would there be a reduction, significant or insignificant, on the ops costs? And again, we're looking at the case where this could be the vehicle for the next 30 years, so ops costs become by far the overall driving factor in the life cycle costs.
Yeah, good. Let me think about that for a minute. I'm trying to think of. So we've done extensive studies on what drives life cycle cost in Orion, and you can imagine a lot of it is the people it takes to build the structure and to build the components. We've done extensive study on what makes sense to reuse in Orion, none of which I think would be driven by the size of the vehicle. Based on our assessments and based on the looks we've done, our intent, we found that the cost trade didn't make sense to reuse the primary structure, but to reuse key expensive avionics and Eclipse boxes. So again, I don't think that is not driven at all by the size of the vehicle. Regardless, you would do those same kind of things. So, so I guess I don't see, again, the pounds we're talking about in decreasing size would not be significant, so I don't see that as really being a cost driver, Sally.
Okay.
Les, and then Jeff.
Mark, the management approach for this program has been a little bit different for NASA than in more recent programs. NASA's the integrator, if you will, has the design and drawing release authority. So the roles are a little bit contrary to perhaps recent major programs. And as our committee went around, we heard some comments and concerns expressed by contractors, probably not surprising, if you will, probably more along the lines of the maturity of the process and some awkward roles and responsibilities issues. I wonder if you could comment if you think one, you had the right role and responsibility. Would you change anything, or are there some lessons learned, or you would do a little differently in that?
Well, let me make sure I'm answering the right question, General. I'm not sure you're talking about Orion. You might be talking about Ares. Can you ask it again? Was it about?
We heard it sort of in general, and
Okay.
Perhaps I'm wrong. Perhaps it's not Orion. Perhaps it's just Ares. But we've heard it in general and talking about the role that NASA plays in management of the overall constellation activities vis-a-vis previous programs.
Yeah, so at a program level, right, NASA has been doing I would say, detailed integrated analysis, which in some of the other programs was actually farmed out or actually allocated to the contractor. Yes, you're right. In Orion itself, it is more of a traditional prime with NASA oversight. So just some notes. So you're talking about the program itself. Probably better answered by Jeff, but I can give you my opinion. I think the stuff that we're talking about, the integrated stack analysis and those kind of things, are things that NASA has a lot of experience based on what we've been doing for the shuttle for a long period of time. So I don't think there's any risk in that. Also, since the way we've contracted these things with, of course, Ares, in order to get the cost and doing the right kind of competition, they're not the same contractor as Orion. So you'd have to pay someone else to be an integrated contractor, and we've seen that issue on Space Station before. When they're not owning the pieces, it doesn't work so well. So I think I thought it was a good strategy, and I think we've seen that so far.
Jeff?
What is, after IOC and all of the initial phasing and tests are done, the ongoing annual and incremental cost of adding Orion missions?
Oh, per flight?
Yeah.
I don't have it off the top of my head. I have to get it to you. You mean, so our current budget shows 2 Orion flights a year, basically the 6 months per flight. So you looking for just Orion or the full
just Orion,
Ares?
No, independent of the issue of the launcher.
Yeah, I have a number in my head, but I'd rather get it officially and get it to you, make sure I got the right number.
Quickly, please.
Okay.
I mean, like.
No, I'll do it before we leave the
today.
building. Yeah,
Thank you.
yeah. Sorry, I just don't want to give you the wrong number.
Bo?
Yeah, hey, Mark, first of all, thank you for a very nice briefing. And my question, please don't interpret my question as some kind of a leaning toward some kind of a launch architecture. It's too early for us to lean anywhere. But the question has to do with, we have been hearing, and some people have talked to us about this potential dual launch architecture. What would that mean to Orion in terms of increasing its size so it can do its own lunar orbit injection, and more importantly, how practical that is? Can you envision, or have you guys looked at what it would take? It's very easy to draw pictures of bigger tanks. I've drawn some of them myself, but is a practical change to Orion to give it delta V capability so it can do its own orbit injection in dual launch scenario?
Yeah, Bo, I guess I'm at a disadvantage. I'm not sure entirely what that architecture looks like and what the assumptions would be for Orion. I know we are optimized for the current plan, where EDS sends us there, the lander gets us in the lunar orbit, and SM sends us back. So it'd have to look at specifically what the changes would be. We do know that the SM, though, is a key part of the abort strategy. It is a key part of how we get the crew off after the last is jettisoned. So any fundamental change to the SM, that has to be integrated into the considerations.
Let me ask you, Jeff, if we wanted to get some feeling of what it would mean to Orion, do we ask you or do we ask Mark?
You can ask him and he'll ask me when we figure out.
Yes. From an integrated architecture perspective, of course, the program would be answerable for the systems engineering and the allocation of the functionality to Mark and to the launch vehicle. And so we at the program level have looked at these potential dual heavy lift launch architectures, and I think what you're suggesting, Bo, is that yes, the Orion service module would have to grow considerably with today's present design. It would grow from about 20 metric tons at the translunar injection point to about double that in terms of its mass. Now, within the capability of a heavy lift launch vehicle, if we build one that's suitable, but now we got to address the ways in which we're complicating the Orion and that massive of a vehicle.
My question really had to do with practicality of that change to Orion.
And that is the part that Mark's at a disadvantage about, because we haven't really asked Orion, hey, if we really had to do this, what would it really take? And that's the part where this has all entered the conversation here just in the last few weeks, and the Orion team's been heads down drive into PDR. So
That's probably a good place to break. We thank you very much, both of you. We will have a chance to hear more about Constellation during the next couple of days and beyond, in fact.